now we're going to talk about gases. So that's what chapter 13 is basically dedicated to. And in this chapter, we'll be examining the behavior of gases and the different laws that govern the behavior of gases. All right. So the theory that is used to explain all the laws that we have observed in gases is the kinetic molecular theory. And basically what the kinetic molecular theory says is that the behavior of gases can be explained by the motions of the gas particles, the molecules or atoms that make up the gas. All right. Now, the gas that behaves exactly as outlined in this theory is called an ideal gas. And even though there are no ideal gases that can be found in nature, real gases can actually behave very close to the behavior of ideal gases under certain conditions of temperature and pressure. So these are the principal assumptions of the kinetic molecular theory. The gas or gases are consisting of very tiny particles, which are the molecules or atoms, and the distance between these particles are large compared to the size of the particles themselves. These particles have no attraction between each other. The particles move in very straight lines, colliding frequently with each other and the walls of the container. No energy is lost by the collision of a gas particle with another gas particle or with the walls of the container. In other words, all the collisions are perfectly elastic. The average kinetic energy of the particles is the same for all gases at the same temperature and pressure, and its value is directly proportional to the temperature expressed in Kelvin. So we can actually write down a formula for the kinetic energy of any moving particle, including gas particles. It's given by this formula. Kinetic energy is equal to half mv squared. And as stated here, all gases have the same kinetic energy at the same temperature. So as a result of that, and based on the equation I just showed you, what you'll find is that lighter molecules will move faster than heavier molecules. And if you take, for example, comparing the hydrogen molecule, which has a mass of approximately 2 AMU, to that of oxygen, which has a mass of approximately 32 AMU, if you were to assume, in fact, let me go here and show you something to illustrate what's happening here. I'm going to open up a PowerPoint page here. And let me do this. Okay, so what I'm going to show you is comparison between the hydrogen molecule and the oxygen molecule. Now, remember the formula we just mentioned. Kinetic energy is equal to half mv squared. Now, what we just said is that for two gases at the same temperature, they'll both exhibit the same amount of kinetic energy. So therefore, if you have an oxygen molecule where the mass of the oxygen molecule is 32 AMU and the mass of the hydrogen molecule is 2 AMU, then we can say that the kinetic energy of the hydrogen molecule will be given by half MO2 times VO2 squared. That would be equal to the energy of the hydrogen molecule, which is half MH2 times VH2 squared. Now, the halves will cancel out, of course, here and here. And if we substitute for oxygen 32 AMU times VO2 squared equals to, for hydrogen we substitute 2 AMU VH2 squared, and the AMU units will cancel out. If we divide both sides by 2, we're going to get 16 here. So therefore, what we'll get here is a ratio of VO2 squared over VH2 squared is equal to 1 over 16. So therefore this implies, if you find the square root of both sides, that VO2 divided by VH2, that will be equal to 1 over 4. Another way of stating it, if I write it up here, is that VH2 will be equal to 4 times VO2. So therefore what this tells us is that the velocity of hydrogen is 4 times faster than the velocity of oxygen at the same temperature. All right? So, and that's in reference, of course, to their molecules. The velocity of the hydrogen molecule will be 4 times faster than the velocity of the oxygen molecules, which makes sense because, after all, hydrogen is a lighter molecule, has a mass of 2 AMU, compared to the oxygen molecule, which has a mass of 32 AMU. All right, so I thought that it illustrates how the molecular speeds compare at the same temperature for two different gases. So that's the relationship right here. The velocity, let me go back to this. The velocity of hydrogen will be 4 times that of oxygen. Okay, so let's talk about how we measure the pressure of a gas. Now, first we have to define what pressure is. Pressure is basically the force applied per unit area. All right, and that's the equation. And as you can see, the units of pressure is dependent on what unit we use for force and what units we use for area. But there are some other units for pressure, which we're going to see shortly, which are very commonly used in science. So we're going to see that as well. So let's talk about how pressure is exerted by a gas using the kinetic molecular theory. So if you remember, we said that the kinetic molecular theory suggests that the particles of a gas are always moving because they're high energetic atoms or molecules. So therefore what happens is that they collide very frequently with the walls of the container. And that collision will result or manifest itself in the exertion of the force across the area of the inner walls of the container, and that's the pressure that will be exerted by the gas. So as you can see in this diagram here, we have a gas trapped in a balloon, and as you can see here, the particles are colliding with the walls of the balloon, and therefore that force resulting from the collision will keep the balloon inflated, and that's the pressure that is exerted by the gas. Now, the pressure exerted by the gas is dependent on several factors, not the least of which the number of gas molecules present, which makes sense. The more molecules you have, the more collision frequency with the walls that the particles will have, and therefore the frequency or the pressure would increase. The temperature of the gas, that makes sense as well. Excuse me. As you increase the temperature, the particles move more quickly, they collide with the walls of the container more frequently, exerting greater pressure. All right. The volume in which a gas is confined, that also makes sense in light of the kinetic molecular theory, because if the container, let's say you could reduce the volume suddenly, then the average distance that the particles will move will be shortened, and therefore they will collide with the walls of the container more frequently, resulting in a greater pressure exerted by the gas. Okay, how do we measure pressure? Well, there are a couple of instruments that we use to measure pressure. The one that is shown here on the screen is what is known as the mercury barometer. Now, they have different levels of complexity in terms of the instrument, but this is the simplest version, and it consists of a tube, which is pretty long, about, well, it has to be greater than 760 millimeters. I'll explain why shortly. You fill it with mercury, and then you invert the filled tube into a trough, which is also containing mercury. And then you leave it to settle for a while, and what will happen is that the mercury level here will fall to a certain height. The height is about 760 millimeters mercury. And what you'll find is that the atmospheric pressure that is exerted on the surface outside of the tube will be enough to support a column of mercury of this height. All right, so basically what you'll find is that if the atmospheric pressure increases, then it pushes up the mercury inside the tube higher, and therefore there's a direct proportional relationship between the atmospheric pressure and the height of the mercury inside the tube. So therefore that led to the unit known as the millimeter mercury unit for measuring pressure. All right, Basically, what that unit involves is the height of the mercury inside the tube. So therefore, we say that 1 atmosphere, which is another unit of measurement, the atmosphere unit, 1 atmosphere is equal to 760 millimeter mercury. All right. So that's what is shown in this table here. 1 atmosphere is equal to 760 millimeter mercury. But there's some other units as well. There's the torr unit. The torr unit is the same, as the torr unit is the same as the millimeter mercury unit. So therefore 1 millimeter mercury is equal to 1 torr. We have some other units here. We have the centimeter mercury unit. That's easy to understand. That comes directly from the millimeter mercury unit. You can convert, I should say, from the millimeter mercury unit to the centimeter mercury unit. And then there's another unit known as the Pascal unit. The Pascal, and you'll see this in a table that I will make available for you in Canvas. Let me just write it down here. 1 Pascal unit is the same thing as 1 Newton per meter squared. All right, and this comes from the equation I showed you before. Remember, the equation I showed you before was pressure is equal to force divided by area. Well, force can be expressed in newtons and area in meters squared. So when the force is in newtons, the area is in meters squared. The units of pressure here would be newtons per meter squared or pascal. All right. And then from that you can have kilopascals, millipascals, whatever. And the relationship here between the pascal and the atmosphere is that 1 pascal is equal to 101,325. 1 atmosphere is equal to 101,325 pascals. All right, so that's another relationship here. And then we can go from pascals to kilopascals. So you see this here, 101.325 kilopascals is equal to 1 atmosphere. Of course, you can get from pascals to kilopascals by dividing by 1,000. And then we have some other units down here, which I honestly doubt very seriously we're going to be using in any of our exercises, like the millibar, the inches mercury, and the pounds per square inch. All right. So those are the different units of pressure that is oftentimes used. Okay, now in terms of the composition of the atmosphere, dry air, this is basically what you see here on the screen. As you can see, the atmosphere, or the air that we breathe, is mostly nitrogen. Almost 80% of it is nitrogen, and the 20% or 21% is oxygen, and the rest are other gases existing in trace amounts. So that's basically the composition of air. Okay, we talked about the dependence of pressure on the number of molecules and temperature. We said that pressure, of course, is exerted by gas molecules continuously colliding with the walls of the container. So if you have a gas at a specific temperature and volume, the number of collisions will be dependent on the number of gas molecules present, as we said before. All right? So for an ideal gas, what you'll find is that the number of collisions is directly proportional to the number of gas molecules present, and that, of course, will be directly proportional to the pressure that is exerted on the walls of the container. So if you look at this diagram here, where we set the volume to be equal to 22.4 liters, and the temperature is at 0 degrees Celsius. For 1 mole of a gas, the pressure exerted will be 1 atmosphere. And then when you double the number of moles of the gas, what happens? The pressure is doubled. When you reduce the pressure, or the number of moles, to 0.5, then the pressure is reduced itself to 0.5 atmospheres, right? So one can see clearly a direct relationship between the number of molecules, which in turn would be related to the number of moles of the gas, and the pressure exerted by the gas. There's a direct linear relationship between the two. Down here shows that it doesn't make a difference what the gas is in terms of its identity. So here we have 1 mole of hydrogen gas here, we have 1 mole of oxygen gas here. They both exert the same pressure of 1 atmosphere under these conditions, all right? And even if you mix the gases together, assuming that they do not react, then basically the pressure exerted would be based on the total number of moles of the gases present. So in this box here, we have 0.5 moles of both oxygen and hydrogen, so they add up to a total of 1 mole of gas, collectively, 1 mole of gases, and the pressure exerted there would be 1 atmosphere under the same conditions. So it doesn't matter if you're dealing with a mixture of gas or if you're dealing with just one gas in the container. If the total moles of gas is 1 mole, then the pressure exerted by either the gas itself, one gas, or the mixture will be 1 atmosphere if the volume is 22.4 liters and the temperature is 0 degrees Celsius. So as stated here, the pressure exerted by the gas is directly proportional to the number of molecules of the gas present. Okay, the pressure is also dependent on the temperature, right? If the volume is fixed, then basically the pressure increases with temperature, and that's because when you increase the temperature, the particles will have more kinetic energy. They will move around more rapidly, colliding with the walls of the container more frequently and with more energy, and therefore the pressure exerted as a result of those frequent collisions will be increasing or increased. And that is shown here in this diagram. So here we have 2 cylinders. This cylinder here is a gas. They didn't say what the gas was, but it doesn't matter. The temperature here is 0 degrees Celsius. The volume is 1 liter. And the number of moles of the gas is 0.1 mole. And the resulting pressure is 2.24. And then we go from this situation to this situation where the temperature changes. The volume and the amount of gas remains the same. But what happens? The temperature increase results in a pressure increase. And we can understand that in light of the kinetic molecular theory, right? So as you increase the temperature, as stated here, the particles move around more frequently, hit the walls of the container more frequently with more energy, and therefore the pressure would increase. All right, so at lower temperature, the pressure of the gas will be lower. At higher temperature, the pressure of the gas will be higher. All right. Okay, so we're going to stop here. So the next video will be a discussion of Boyle's law, which will be the first of a series of laws that we're going to discuss. All right, so until next time.